Good morning students. Before everything, I congratulate all of you for your active participation in this online classes. It's happier when you text us for the queries or when you suggest us for the betterment of the videos. Keep it up, go on the same way. Okay. So, moving on, keeping a next step in the current electricity. In today's class, we will study some more new topics about current electricity. So friends, from last 2 to 3 videos, we are studying about current electricity. In that, we have covered so many interesting and important topics. Okay, I hope all of you are perfect in all of them. Okay, so if you want to revise the things, you already have the videos. Keep them watching often and often. Okay, so today in this chapter, we will study about some further steps. I'll start today's class with 3 more important definitions. Okay, before that, let's think what are the things we have studied. We started with the definition of electric current. We got its expression and we have obtained the SI unit for it. After that, we studied the phenomena or the physical phenomena where the electrons are moving and constituting the electric current. After that, we gone through the important properties of moving electrons like drift velocity, mobility we have studied. After that, we studied the important law, that's Ohm's law, and we have explained it thoroughly. In that, so many concepts like resistance, resistivity, everything we have covered. Okay, so in today's video, I'll start with the 3 important definitions. So what are those? I'll start with the current density, conductance and conductivity. Let's go one by one. Okay, so current density means the word current is familiar to you. So what will be the current density means you just consider one conductor now. So what happens in the conductor? Electrons are moving from positive to negative direction and hence they are constituting a current. Okay, so any one conductor if you consider, let's consider this as a conductor. So in this conductor, electrons are moving in this direction and the electric field is moving in this direction, that we studied in detail in the last videos. Okay, so this conductor is having some particular area, isn't it? This conductor is having particular dimensions. Among them, area is one dimension. So in this conductor, when the current is flowing with respect to its area. So at that time we will get the current density in this conductor. So how can we define current density? The current flowing in a conductor per unit area of the conductor. So what we can define the current density as? The current moving in a conductor per unit area of the conductor. Current density means current moving in a conductor per unit area. Understood? So this is the definition of current density, and current density we can denote by the letter J. So how we have defined it? The current density is nothing but current moving in a conductor per unit area of the conductor. Understood? Just simple definition is there. Okay, so by this expression you can think of what will be the SI unit for current density. So we have current over here and we have area. So the unit of current is ampere and area you can measure in terms of meter square or centimeter square. So the SI unit of current density is ampere per meter square. Understood? So this is all about current density, and current density is a vector quantity. It's having its own direction. It's not scalar, it's a vector quantity. Okay, so this was the first definition. Okay, so next I'll go with the 2 more definitions, conductance and conductivity. So I'll try to explain it in an easy way. You already know about the resistance. So what is the resistance? When in a conductor electrons are moving, there creates an opposition. Like in this conductor, if electrons are moving in their own way, there creates some opposition. Because of the collision between electrons and ions, there creates an opposition. That opposition is nothing but what? Resistance. So what if there is no opposition? If there is no opposition, the electrons will move in their own way without any disturbance. The electrons are moving current is moving, current is conducting in this conductor. So if there is no resistance, there is conductance. If there is no resistance, if there is no any disturbance, electrons are moving, current is conducting in this conductor. So no resistance, there happens conductance. So how can we define conductance? Conductance is nothing but inverse of resistance. There is no resistance means there is conductance. There is no conductance means there is resistance. So we can define conductance as it is a property which is inverse of resistance. So resistance is denoted by R and conductance is denoted by the letter G. So how can I write the expression for G? 1 divided by R. So how I have defined it? The conductance is defined as inverse of resistance. Okay. So as we have resistance, we also have resistivity. So with respect to resistivity, we have conductivity. So this conductivity is denoted by the letter sigma, and resistivity you know that is rho, 1 by rho. Conductance is inverse of resistance. Conductivity is inverse of resistivity. Understood? So conductivity can be defined as the inverse of resistivity. Okay. So now think of the SI units for conductance and conductivity. So for the resistance, what is the SI unit you have? Ohm you have. What you have? Ohm. So its inverse. See. Is it inverse of this symbol? And the inverse of OHM. Ohm is MHO. Mho. Understood? So the conductance is having a SI unit mho, and the symbol is this inverted ohm. Inverted ohm, or you can say it as mho. Or sometimes the conductance is also measured in terms of the unit Siemens, which is denoted by the letter S. So the SI unit of conductance is mho or Siemens. Similarly, so for the conductivity, what we have? Resistivity, what we have? Ohm meter. Ohm meter you have. So for the conductivity, what you have? Per ohm per meter, because it comes 1 divided by ohm meter, na? So per ohm per meter. So here also you can write it as a per ohm. So it's just inverse. So conductance is inverse of resistance. Its SI unit is mho or per ohm or Siemens. Yes. And the conductivity is inverse of resistivity. Its SI unit is per ohm per meter. Understood? So these are the two important properties or two important definitions we are studying over here. So we have studied about current density, conductance and conductivity. Simple definitions. Okay. So that conductivity, what we studied, sigma, it's having its own expression. So what is that expression? We need to know. And you know, to get the expression, what we have to do? Derivation. So in physics, what happens? If you walk on the track of derivation, you will get a destination expression. So to get the expression for sigma, we have to do derivation. This is what happens in physics always. So to get the expression of sigma, we have to do one derivation. To get the expression of sigma. Okay. So for that, what I will do? We have already studied current, drift velocity, all the things we have studied. So if you think of I, for I, you have so many equations. You have I is equal to Q into T, you have I is equal to NEA VD, you have I is equal to V by R. So in among them, I use one expression NEA into VD. So what is this expression? Try to remember. It's a relation between current and drift velocity. For that we have done one derivation there. Okay. Don't forget the things. I is equal to NEA VD. So okay. So instead of this VD, we can replace the VD as VD is equal to E into sigma into tau divided by M. So here also what I am doing, I am considering a conductor. That conductor is having a length L, it's having an area A, it is having an electric field E and the potential difference V, and in this conductor current I is moving. Okay, so by that assumption only I have considered I is equal to NEA into VD, where N is number of electrons moving in this conductor per unit volume. Okay, so this in this expression I replace VD by E into into tau divided by M. So what happens to the expression? N E A tau divided by M. Okay, so see here we have N is number of free electrons per unit volume, E is charge of the electron, area, electric field, relaxation time and mass of the electron. So here E, this electric field E, we can replace it by V divided by L, electric field in terms of potential. So what happens now? N E square A tau divided by M, E is replaced by V divided by L. Okay, so now what I am taking? I am considering the ratio of V by I by this expression. So what happens? We keep it as it is, take I to this side. So all these remaining quantities will move to the opposite side. So what we'll have? ML divided by N E square A into tau. Okay, so what I did, I just taken the ratio of V and I. Okay, so this V and I can be replaced by R. The ratio of the potential difference to the current flowing is nothing but resistance. Okay, so now I'll just adjust the terms N E square tau into L divided by A. Just rearrange the terms. Okay, so have you seen this expression ever before? So see here, R is equal to M divided by N E square tau into L by A. Okay, I'll make it simple for you. Rho divided by L by A. You got it now? So when we are studying about dependence of R, we have got this expression, and by this only we have obtained resistivity. So does this is these two equations are similar to each other? R is there, L by A is there, and instead of resistivity we have one term here. So what we have there? Rho is equal to M divided by N E square tau. So this is what expression for resistivity we obtained. Okay, so but here what we are expecting? We are expecting the derivation for expression of conductivity, and we have got here resistivity. So you know conductivity and resistivity are inverse of each other. So rho is equal to M divided by N E square tau. By taking this only we can write sigma is equal to N E square tau divided by M. Isn't it? Because sigma is equal to 1 by rho, or rho is equal to 1 by sigma. So I just inverted the equation. So sigma is equal to N E square tau divided by M. So this is the expression for electrical conductivity we obtained. So what is the expression we obtained over there? Sigma is equal to N E square tau divided by M. This is the important equation which is more useful for you while solving the problems. Okay. So we have studied about current density, conductance and conductivity, and we obtained the expression for conductivity. Okay. Moving on. So when we studied Ohm's law, we have obtained one expression there. What we obtained? V is equal to I into R. So this is what? A universal expression which explains the Ohm's law. Okay. So by keeping the Ohm's law original as it is, we can study it in different forms also. Means different form means now I am teaching you. I am giving a lecture on the current electricity. I have my own way of teaching. I have my own passion of teaching. Okay. So I can deliver this lecture in different forms also. Like I can teach you in a very slow manner, or I can teach you in a very fast speed, or I can teach you in different languages. Means what? The teaching material will be the same, the meaning will be the same, but the way of delivering the lecture will be different. Means I will teach you in different forms. Like that, Ohm's law will be the same. it is not changed, it is unchanged. Original is the same, meaning is same, but we can study it in different forms. Like V is equal to IR is there na, the parameters we can change, but the meaning remains the same. The form just changes. So here what I am going to do, I am going to tell you one new form of Ohm's law. Instead of using V of IR, we can use another expression also, that is called as equivalent form of Ohm's law. What's that? Equivalent form of Ohm's law. Without changing the meaning, we study Ohm's law in a different form. Understood? So for that also what I'll do, I'll consider I is equal to NEA into VD, and VD is replaced by, what VD is replaced by? E into E tau divided by M. So what happens? N E square A E tau divided by M. Okay, so by keeping all the things on that side only, I'll take this A to this side. I divided by A, and N E square E tau divided by M. Okay, so I by A, this ratio we have studied na in the first definition only. That's nothing but what? Current density. I by A is nothing but what? Current density J. And I'll keep this E on this another side. N E square tau divided by M. So this is nothing but, what is this? Conductivity. We have just derived that. So J is equal to sigma into E, we can write. J is equal to sigma into E. So this is equivalent form of Ohm's law. Instead of V of IR, we can also study Ohm's law in this term. Like, so what in V is equal to IR, what we did? We get V is directly proportional to I. So remove the proportionality sign and use the constant over there. So here also the same. J is directly proportional to E. The current density is directly proportional to electric field, and to remove the sign, proportionality sign, we used sigma as a constant. So this is an equivalent form of Ohm's law. Okay. So while studying about resistivity, we studied its dependence. How resistivity depends on temperature we studied. So we have got one parameter over there, that is called as a temperature coefficient of resistivity, and also we have given expression for this as rho minus rho naught divided by rho naught into T minus T naught. The same way, so here we got the temperature coefficient of resistivity. One more is there, temperature coefficient of resistance. So how can we write it? R minus R naught divided by R naught into delta T. So this is temperature coefficient of resistance. This is temperature coefficient of resistivity. You just consider this as alpha bar. In your notes also you change it by alpha bar. So these two things we are going to use while solving the problems. For that purpose they are useful. Temperature coefficient of resistivity and temperature coefficient of resistance. Okay. So this completes one small bit in current electricity. Okay. So now moving on to the next things. So in the previous classes we have studied about the devices which opposes the flow of electrons in the conductor. What those devices are called as? I have shown it to you. They are resistors. Okay. So we have studied thoroughly about the resistors in the previous classes. We have also studied how to read the color bands on the resistor. How to obtain the values of that resistor also we have discussed in the last class with the interesting pattern called as color coding of the resistors. Okay. So what happens if you combine the two or more resistors? Okay. So if this is a single resistor, so I can combine the two resistors. One resistor, two resistor, third resistor. Like that we can combine the resistors with each other. That we study under combination of resistors. Okay. So but before going to that, two important definitions we have to study. Electric energy and electric power. Electric energy and electric power we have to study. So electric energy is nothing but what? Before going to the definition, let's explain it first. Now you consider one current element, or you consider any electric device like heater, electric lamp, anything. Let's consider this is one electric device. So in this electric device, current is flowing, current I is flowing from the end A to end B. In this electric device, current is flowing from A to B, and Q number of charges are moving in a time T. So what we can write Q as? Q is equal to I into T. Okay. So but if V is the potential difference between A and B, if V is the potential difference between A and B, we have to consider the work done in bringing the charge from A to B. Like in the second chapter of your syllabus, you will study about the electric potential. Means if Q is a point charge and is having its own electric field in it, and another charge Q1 is there, or you can say unit charge is there. If you want to bring this charge from infinity to any point in this conductor, there should be one work done. There should be a work done called as electric potential. That we'll study in the second chapter in detail. But here also what I am telling, if you want to shift a charge from A to B, there should be a work done. That work done is given by W. Means you are bringing the charge from A to B. For that, whatever the work is done, that is called as V is equal to W is equal to V into Q. Okay. So already we have got Q. So what is Q? Q is equal to I into T. So W is work done in bringing a charge from A to B. And whatever the work done is nothing but energy consumed. Like if you have energy in your body, then only you will do the work. So whatever the energy you have, the same work you will do. Means if you are weak, you will do less work. If you are strong, you will do more work. Means the energy consumed is always equal to the work done. So here work done is always equal to the energy consumed in this network. So what we can write? E is equal to VIT. So this is energy, electric energy of this electrical network. So how can we define the electric energy? The work done by a source. Means, so in this conductor, if current is flowing, means how the current is flowing? You are connected with some battery here, then only current is flowing. This battery is doing work to make the current flow in this circuit. So how can we define the electric energy? The work done by the source to maintain current in the electrical network. The work done by the source to maintain electric current in this electrical network is nothing but electrical energy. Understood? Similarly, we have electrical power also. Electrical power is nothing but the energy per unit time, or the work done with respect to the time. So you already know E is equal to VIT, and also this E is equal to VIT is there. Na? We can study this in two different forms again. How? E is equal to VIT you have. The first way is, instead of V, by the Ohm's law what we have, V is equal to I into R, and I is equal to V by R. So use the first thing. E is equal to VIT is there. Na? Instead of V you use IR. So what E is equal to? Instead of V I am using IR and I into T. So E is equal to I square R T. So this is the first form of electric energy. Similarly, for the second you use this. I is equal to V by R. VIT is there. Na? V, in the place of R you use V by R into T. So what you get, E is equal to V square by R into T. So E is equal to I square RT and E is equal to V square by RT are the two different forms of electrical energy. Let's write them. V is equal to I square RT and E is equal to V square by R into T. While studying the electric power, we use these both expressions. Okay, so what I told you, electric power is nothing but energy per unit time, or the work done per unit time. Okay, so you use, instead of E, you use the first form of electric energy there, I square R T divided by T. So you have P is equal to I square into R. In the now you use the next thing. Next what we have, P is equal to A by T. In the place of E, V square divided by R into T. V square divided by R into T. Okay. So already, and one more T you are having here. So T get cancels. P is equal to V by R into V. V square is there, just I written it, V into V. So V by R is nothing but what? According to Ohm's law, it's I. So what we have for the electric power? For the electric power, we can define it as the product of applied electric field and current flowing in the conductor. So how can we define electric power as? The electric power is defined as the product of applied electric field and the current flowing across the conductor. Understood? So these are the two important definitions. Okay. So next, we'll study, I have already told you, we'll study what happens when we combine the resistors. Okay, we can combine the resistor series wise like this, end to end, or also we can combine them like this, means parallel to each other. Series combination, parallel combination. Okay, so about that also we have so many things to study. So instead of using two resistors, you can use a single resistor which will give you the same effect. Means this combination can be replaced by a single resistor. That is called as a effective resistor or equivalent resistor. Okay, series combination, parallel combination, equivalent resistor, all the things are there to study. So I will continue the remaining things in the next class. Okay, stay connected with all the things whatever are discussing over here, and as usual if you have any doubts you can contact me. Okay, thank you.